You're here because you want to master electrochemical cells with a University of Cambridge graduate. Let's begin. Electrochemical cells are actually the first part to understand electrochemistry as a whole. And from this chapter, you will understand how your chemical reactions drive the movement of electrons in the whole electrochemical cell. Now, if you want a free copy of my notes, be sure to hit the link below so that you can download a free copy for yourself. You can use my notes to follow my lecture closely, and hopefully it will help you overall in your revision for your A-level chemistry. So for your electrochemical cells, you have to understand how to draw this whole setup over here. So this is a very typical setup of your electrochemical cell or your galvanic cell. Seems like a lot? Well, let me break this down for you to very simple, easy to understand pieces. So over here, you have two beakers. So let's just take a look at one of them, starting with the one on the left. Each of these beakers make up a half cell, and two halves make a whole electrochemical cell. If you focus on each of these half cells, you'll realize that each half cell has the necessary things required in order for a reaction to occur within that half cell. So you will see that I have put in the necessary ions or atoms that will be used or will be reacting in that half cell itself. In this case, on the left, we'll have copper and the copper 2+ ion. So I make sure that in my half cell there's a copper 2+ ion. So in my copper nitrate solution I have copper 2+, and I have copper metal as well, which is the electrode as well, the copper rod. Now you can see on the right you have the same thing. So I have zinc 2+ and zinc over here that will be the main reagents or the main actors in my whole half cell. So I have zinc sulfate over here that provides the zinc 2+, and you have zinc rod over here that provides the zinc solid, right? And then I just connect a bunch of wires to both electrodes over here, and I have a voltmeter over here as well that helps to measure the potential difference between the two half cells. Then I also have a salt bridge. So what does a salt bridge do? I get this question a lot. A lot of students ask me this question. So a salt bridge is actually meant to prevent mixing of your both solutions while still letting ions pass through. Again, you need a whole circuit so that electricity can flow through, or your electrons can also keep flowing. Now, this is also helping to keep your solutions electrically neutral as well, because if you don't really have a salt bridge, right, what's going to happen is the two reactions are going to keep going, and then you will have a build-up of charges, and when you have a build-up of charges, your reactions might not continue. So that's where your salt bridge comes in handy as well. You don't need to memorize this whole definition of a salt bridge. It's not really tested in exams. So if you go back to the diagram, you will realize that both your half cells have reactions as well, that in each of their half cells. Okay, so you can have Cu2+ that gets reduced to Cu, or you can have zinc solid that gets oxidized to zinc 2+. These are the two reactions that happen, and you have to categorize each of these reactions. So one of them is reduction and one of them is oxidation. Eventually you'll learn how to figure out which half cell has the reduction and which half cell has the oxidation. So the place with reduction is actually the cathode, and the place with oxidation is actually the anode over here. So once you've broken all this down, here you can fully understand the whole electrochemical setup, and you can have an overall reaction as well from this whole electrochemical setup. So the overall reaction, okay, will just be Cu2+ after balancing the electrons, but thankfully they have the same number of electrons. And this is the reaction. So you can use these reactions in each of these half cell to justify some of the observations that you would see as the electrochemical cell is going. So for example, in the left, right, you know that Cu2+ reacts to give Cu solid. So the Cu solid will become pink solid deposits on the electrode. You can also see the electrodes start to get heavier, and because Cu2+ is reacted away, you'll see the solution become less blue. This is one potential observation. And on the right, you'll see that zinc solid, okay, becomes zinc 2+. So actually your zinc rod, okay, so your zinc rod will be smaller or will decrease in mass. So overall, whenever I'm trying to understand the whole electrochemical setup, you have to follow those steps in order in order to understand what are some of the reactions that happen in each of the half cells. And then overall, you have an overall reaction, and you also from there know who is the cathode and who is the anode. Next up, let's discuss electrode potential. Electrode potential is basically the E values for the half cell. Now, for a reaction like this, for example, Mn plus Ne minus giving M solid, this is actually a reversible reaction. In fact, all your electrochemical reactions tend to be reversible, and this E value would determine the position of equilibrium. So if you have a positive E, it means that the position of equilibrium lies to the right and reduction is favored. And if you have a negative E, the position of equilibrium lies to the left and oxidation is favored. Now I can say this confidently where the position of equilibrium is, and that is because it's very standard practice to write your equations for electrochemistry in the reducing manner from left to right. So you'll see over here that from left to right over here is actually a reduction, and from right to left it will be oxidation. So because of that, it's very easy to determine the position of equilibrium just from the E value as well. Now, what are some of the factors that affect your electrode potential? Well, because as I've said that all these reactions are reversible, right? You can refer to my chemical equilibrium master class. And basically, all the factors that affect your position of equilibrium will affect the electrode potential. So for example, your concentration of ions. If you have a concentration higher on one side than the other, then obviously the position of equilibrium will move, affecting the E value, right? Your temperature could affect it, depending on your endothermic or your exothermic reactions. Your pressure of gases, of course, if gases are involved, which they can be in electrochemistry, then obviously this will all affect the E value. Now, how do I actually measure my electrode potentials? Well, you can start off by understanding what is the standard electrode potential. So this standard electrode potential, the E naught, okay, this naught over here, this is the relative potential of your electrode under standard conditions compared to the standard hydrogen electrode, or SHE, okay, that has an assigned 0V. So because there's an assigned 0V, everything is relative to this standard hydrogen electrode. Now I'll be explaining what this standard hydrogen electrode is. So this is basically the setup for the standard hydrogen electrode. It consists of H2 gas at 1 bar, okay, and it's bubbling over this platinum electrode coated with finely divided platinum that is dipped into this 1 mole per dm cube H plus aqueous solution. So this would be the half of the cell that is used, and you must know how to draw. You must know how to draw this. It's very important. And don't worry, it's actually easier. Just takes a couple of practices, right? But you just need to make sure that all these conditions are there, because this is what determines the standard conditions. Now, because this standard hydrogen electrode has 0V, right, you can slap this onto any other half cell, and you can determine from the potential difference the E value of the other half cell. So the reaction that happens here is obviously 2H plus that is being reduced to give H2 gas. It gets very simple, and it's actually found in your data booklet as well. So again, for measuring E naught, right, remember that all the standard conditions must apply. So your solutions must be at 1 mole per dm cube, your gases must be at 1 bar pressure. Okay, your electrode must be this platinum unless you use the metal solid. You use a metal electrode, basically like copper, right? And your temperature must be at 298 K, and yeah, you must know how to draw the whole thing. So this is a typical example of how you draw it. For example, if I'm trying to know the reaction of this M metal over here, right, I have to set it up in that way. Now, if you have half cells with gases involved, so for example with Cl2 basically and Cl minus, so your Cl2 can be reduced to Cl minus, well then you have to set it up accordingly. So you have to use like Cl2 gas with 1 bar pressure, right, and also 1 mole per dm cube Cl minus. So basically all these standard conditions have to apply. Of course, it's all at 298 K as well. And the other half cell will just be this standard hydrogen electrode. Now take note of some of the cell notations as well. You might be asked to draw it or interpret it from whatever they give you. So these are the notations used. Basically this one liner over here is the boundary between two faces, and this two liner is the salt bridge, so that's easy to know. And this comma is just the two oxidation states sharing the same homogeneous aqueous phase. So for example over here, if I have a reaction, I have an electrochemical cell like this, right? we can decipher that the cell notation is actually like this, okay? And this is because the left side is usually the anode. Okay, this is the part that oxidizes, and I know my zinc solid oxidizes is zinc 2+, okay, and my cathode is on the right side. If you use a non-metal in your half cell, you will need a platinum electrode instead. So for example, this is how you draw the cell notation, right? So let's say you use a standard hydrogen electrode over here. So this uses a platinum electrode, so this requires one line over here because it's two different phases, and another line over here, two different phases between the solid and the gas and the aqueous phase, right? Followed by the salt bridge, right? And then if you have two, let's say you have this iron 3+ and iron 2+ half cell, right? Then you use a comma over here. So this is one of the ways. So this is like two different oxidation states, but they're in the same aqueous phase. So from all of this, you can also determine the standard cell potential. So this is the E0 cell. This is the overall cell potential, like mixing the two half cells together, right? And this is actually the electromotive force of your electrochemical cells that consists of the two half cells under standard condition. Again, standard is very important because we're talking about standard cell potential. Now, the E0 cell value, this is the difference between the two standard electrode potentials. So how do I calculate my E0 cell? Well, this is E0 cell, it just follows this equation over here. It's E0 red minus E0 ox. So basically the half cell with reduction minus the half cell with oxidation. And I'll just follow this equation. So for example, if I have a half cell like this, first I have to determine the reactions that are involved in both half cells. So this would be the reactions over here, and I find out the E0 values over here. So these E0 values are set, right? And then I just have to plug it into the equation over here, and I get my overall E0 cell, right? And from the E0 cell, why is this so important to know how to determine my E0 cell? Well, this is because you can predict your feasibility of your reactions with E0 cell. So for example, your redox reactions, your feasibility, if you have a positive E0 cell, this means the reaction is spontaneous. And then if E0 cell is negative, means it's not spontaneous. And if it's equals 0, means the equilibrium is established. Now this sounds very familiar, right? Well, later I'll show you how this is a relationship between delta G and E. But what are some of the limitations of using your standard electrode potential to determine feasibility? Well, you can tell feasibility, but again, similar to delta G actually, you cannot tell the rate of the reaction. You can't tell the kinetic properties of the whole reaction, right? And again, your E0 requires very standard conditions. So if there's any change to the standard conditions, right, definitely it will affect the E0 value. Now, the relationship between delta G and your E is actually delta G naught, okay, is equals to negative NFE. Right, this is an equation that you must memorize because you'll be asked to apply this equation. Okay, N is your mole, F is your Faraday constant, which is actually 96500, and then E is just the E value of the whole cell. So put this all inside and you get a delta G in joules per mole. Now, one small thing that you have to know as well is that nowadays with these electrochemical cells, we're actually moving towards development of improved batteries, right? So we're moving towards a trend of smaller size, lower mass, higher voltage, lower cost, long shelf life. So these might be some of the advantages to some of the cells that you might be tested on during the exam when it comes to applications. So just take note of some of these advantages that comes along with it. And this is also a preface to saying that there will be some weird cells that come out during your exam. But again, if we scroll back to the beginning, everything hinges based off there's a cathode and there's an anode, and you just have to slowly figure out what are the reactions that happen at each, the cathode and the anode. Hopefully I did a very quick summary for you so that you can use this for your revisions. Again, this has very close ties to chemical equilibria, so be sure to refer to my chemical equilibria masterclass if you need a recap on any of the chemical equilibria concepts. If you like this kind of content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my chemistry tuition class, be sure to hit the link below so that you can book a free call with me and I can run through any doubts and clarifications you may have and go through for free your past exam paper. And I will also show you why my class is the best fit for you. I'll see you in the next lesson.